Okay, hi. My name is Amrit. I handle operations at AltLayer. This is going to be a very high-level talk, so I'm not going to go deeper into how some of these systems are built. We'll give you some ideas of what we can do with hardware, especially around verifiability and what are these different areas where we can apply them. Um, so let's start with agents, since everyone talks about agents and AI and whatnot. Um, and if you think about agents, right, there are three different ways in which you could be using agents. So the first one is could be a setting where this agent has been built and customized for you as a specific user. So imagine, like, I don't know, you want to go to gym or you want to cut down your weight or whatnot. You build an agent that is designed to propose a custom setup for you that you follow, or a custom regime for you that you follow. The second one could be a model where this agent has been integrated into a certain service or product. So imagine something like Aave or Compound or whatever, right? So you have this agent that is built right into a certain DApp or a service, and that service looks at your, for example, your past transactions and whatnot, or looks at some of the system parameters and makes suggestions on certain activities or certain transactions. The third one is a model which is much more public. Consider something like ChatGPT, which is an agent that's available to anyone. It's not necessarily customized for any specific use case, but then you could still use it more directly. No matter what form you use your agent, or no matter what form your agent takes, you need some kind of verifiability. The reason is, like, imagine, let's say you're using an agent to manage your hyperliquid positions, for example. How do you make sure that this agent is actually going to do what you expect it to do when shit hits fan, right? So, for example, let's say your liquidation is getting, you're approaching your liquidation threshold, and you want this agent to actually take an action. You want to make sure this agent is doing what it's supposed to do. The second scenario where, for example, you have this integrated in an app or a service. So imagine like Ethereum, right? So if you're running an app on Ethereum, the reason why it works in many ways is because you have this app, and that app runs on a decentralized system, and this decentralized system gives you proof or some sort of a guarantee that this contract is being executed correctly. And because of that, then you can compose with other applications, right, on the same platform. So Ethereum gives you this base trust layer. What is this trust layer when you have agents interacting with each other? Right? So imagine, like, you have this Aave agent that does something, and this, let's say, this Uniswap agent is supposed to kind of take data from this Aave agent and then supposed to do something on a Uniswap. How does this Uniswap agent get a guarantee that this Aave agent is indeed doing what it's supposed to do? So you need this verifiability to allow for composability, right? If you don't have verifiability, you cannot compose. It's as simple as that. And therefore, you need some sort of a verifiability. How do you make sure that this agent is actually doing what it's supposed to do? Now, what does mean by, like, verifiability in an agent context? The first one, what we call non-interference, which basically means that here is this agent, and no matter who's running this agent, he cannot modify the outcome or the output that comes out of this agent. So there's no interference in terms of the output that is supposed to generate. The second one is tampering, which is like, if this is the code that the agent is supposed to run, then that code has not been modified, right? So it's a very core of the agent remains intact. Now there are different places or avenues where you want this verifiability. The first one is, of course, deployment. So when this agent is being deployed somewhere, and you as a user, you want to use this agent, you want to make sure that this agent code is exactly the same code that is supposed to be running. So you want this verifiability at the deployment stage, because if you can't even guarantee that, then everything after that basically falls apart. The second part is invocation. So imagine you make a request for some sort of inference from this agent. You want to make sure that what output comes out from this agent is indeed coming from that specific code or that specific logic. And the third one is updates. So, of course, agents will get updated over time. So you may have an agent that does something today, and then maybe its feature set gets expanded, and maybe tomorrow it does something else, or maybe does something more. And how do you make sure those upgrades or updates are being reflected, and you as a user can verify that it's not a malicious upgrade or update? So you need this verifiability at these distinct levels of this software cycle. So how do you, and of course there are different ways of getting this verifiability. Of course, people are trying, for example, ZKML and whatnot. And one simple way to achieve this right now, today, is through, for example, hardware, like Intel SGX and the likes. Of course, then you're trusting the hardware, trusting the manufacturer, trusting where these hardware sit and everything that comes with it. But one simple way to do this is basically you have this, let's say, TE prover, and you have, for example, imagine on-chain contract, and then you initiate the enclave. You get this addition report that goes to this contract, or end user verifies that this is the actual code that's going to run in this hardware, and then you send a task to the system. The system responds to you back, and then you verify that the system is operating correctly. Of course, this is not the only way you get verifiability. There are different other ways. As I said, you can use ZK, but it's something that, of course, ZK is not available right now in the way you'd want to use it for different kind of systems out there. So this is something which you can use interim today right now. The second one, which is interesting, is on the blockchain side of things. So this part covers like how do you make our rollups more robust. So for those who don't know, rollups are basically a mechanism, an off-chain mechanism that allows you to process transactions much faster than an existing L1 like Ethereum. So you have a node or a system called sequencer that takes transactions from end users, orders them in a certain way, and then passes those ordered set of transactions to this node that is called executor that executes transactions in that specific order. And those transactions on the final state then goes back to a settlement layer, or Ethereum in this case, and then people can challenge or say whether this state is valid. Okay, so basically there are different stages of rollups, or how you assess or categorize different rollups. So the first one is called stage 0 rollup. This is by the definition that came in, I don't know, 2-3 years ago, proposed by Vitalik. And the high-level idea in this stage 0 rollup is that it's a rollup where basically the definition is very, very weak. And what they expect you to do in stage, if you want to be categorized stage 0 rollup, is first is you have to call yourself a rollup. So as long as you call yourself a rollup, you at least meet the first requirement. The second requirement is that you should send transactions on Ethereum, which is a account we have been debating over the last, I don't know, year or so. What exactly is a rollup? If you use Celestia or EigenDA, do you consider yourself a rollup? And the definition is no, you should not be called a rollup if you do not post transactions on Ethereum. And the third one is that users should be able to push transactions on their own. That's one more criteria, which is like if your sequencer is down, or if any node in the service is down, you still should have this ability to push transactions directly to the L1. But there's no requirement on either fraud proofs or validity proofs. So there's no security guarantee per se. So you're not required to have any of these security guarantees. So basically, this means that this chain is basically running with full training wheels, right? The second stage is what's called stage 1, which has limited training wheels. This is where you're required to have fraud proofs. It does not necessarily need to be permissionless. For example, you could have, let's say, I don't know, a selected group of nodes or operators that are allowed to challenge an invalid state transition function, but you need to have fraud proofs. And of course, calling yourself rollup is not enough. But that's one of the main requirements. The second requirement is around this upgrades. So imagine if, let's say, you want to push upgrades to your rollup. So for example, let's say you want to modify, put a new opcode, or you want to modify how your bridge contract works, you need to have some sort of security council, which is like a multisig. It could be, I don't know, 3, I think it's recommended to be 6 out of 8 or something. So there's a multisig that is allowed to make upgrades to the system through voting. So basically, it's controlled by this 6 or 8 group of people, and they can arbitrarily change whatever they want. So this is a risk. You still have training wheels in the sense that if you have to push upgrades, you have this security committee that can actually take actions. Let me check if do we have text. Okay, we have text. I don't know what's happening. Things are okay. The third one is the stage 2 stage of rollup, where basically the requirement is that you can have the security council, but is not allowed to make modifications. So so basically the security council is only allowed to judge whether a certain state proof is actually valid or not. So for example, the way you would do it is, let's say, for example, you're building an optimistic rollup. So you have this optimistic, let's say, executor that executes transactions, and then you have on the side some other implementation. It could be a ZK, which is something that, let's say, Optimism is trying to do. Scroll tried to do that as well with TE proofs, where you have some other implementation, some other client, and that client basically reruns the transaction or does some other execution, and then the security council only compares the results. So you could say that, okay, if one of the, let's say, proof system is buggy, then you could use an alternative proof system to actually detect that something went wrong. But security council is not allowed to push upgrades unilaterally. Okay, so if you look at, by the way, this is not necessarily updated, but if you look at the state of all the rollups out there in the market today, The top ones, including the likes of Arbitrum and OP and Base, they are actually not at stage 2 at all. In fact, if you go and check, right, I think, I'm not sure when this was changed, but if you look at today, if you go to the website today, L2Beats, OP mainnet is being downgraded from stage 1 to stage 0 in the next 30 days or so, apparently. So basically, Arbitrum 1 is the only major chain rollup that is considered stage 1 today. By the way, there are some stage 2 rollups, but they're not, probably you would have never heard of them. But there are, I think, two or three stage 2 rollups that are actually right now live, but they're not the big ones. Oh, it's really missing everything. Okay, I'm not sure what's going on. So if you compare Optimism and Arbitrum, the main thing that's missing, that's preventing them to go to stage 2, is this idea that you need to restrict the power of the Security Council to basically judge whether two different implementations of the state transition functions are actually matching. And so that's the only piece that's basically missing in both contexts. And the way you do this is by, okay, so if you want to restrict the power of the Security Council, you want to have at least two different implementations of your chain, of your state transition function. So you could have, let's say, a classical, let's say, optimistic rollup where you have this full node or this executor that takes transaction from the sequencer and processes them, or you could have, and then you have this optimistic fraud proof mechanism, or you have on the side, you must have some sort of a ZK proof mechanism where it actually takes transaction and produces a proof. So even if there's a bug in any of these systems, actually you can compare eventually whether the two systems actually agree or not. The only challenge is, like, if you start bringing ZK provers, then it becomes more expensive to run those rollups. And so the alternative is, again, to bring TEs. So you have, as I said, if you want to have the Security Council has to have limited powers, so it will only do dispute resolutions. And the way you do it, you have, let's say, 2 or 3 implementation of your transition functions, and then basically you compare. So how would you get to using TE here? Again, it's very simple. The way you do it, you have like a full node being run in some sort of TE, and then you take transactions, send that to the TE prover. The TE prover will then execute those transactions and produce your proof that you can compare. Again, you do not fully rely on the TE prover as your security assumption. You're basically relying on your optimistic game, the challenge game. But then, if you want to restrict the powers of your Security Council, you then can rely on the output that comes from TE proof, and you can compare that with your existing fraud proof system. Do we still have time? Let me check. 5 minutes. Okay. So I think I'm towards the end of this thing, and so I'll put one more application of hardware, which I feel really interesting, and some people are actually working on it, which is this idea that if you look at systems like Bitcoin, when it was proposed back in the day, it was designed and promoted as a P2P digital currency, where the idea is like, I can transfer assets to you without relying on any central party for auditing and for maintaining this account balance for you. But if you think about it, right, the Bitcoin network, or any network for that matter, is actually not P2P. What I mean by this is, like, the network is P2P in the sense that, yes, there are nodes in the network that actually communicate with each other to agree, or run consensus protocol to agree on the final state of the system. But when you, as a user, when you are transacting or sending Bitcoin to someone, your transaction actually doesn't get settled in a P2P way. So imagine something like physical cash, right? Of course, physical cash gets minted by some banking authority or minting authority. But once the cash is in your hand, when I give cash to you, that transaction gets settled between you and me directly. That doesn't happen with any blockchain systems today. So in that sense, the Bitcoin network or Ethereum network, they are P2P networks, but the final system that's built on top, that's not P2P. So the question is, can you actually achieve a truly P2P system where I would be able to convince you that the digital asset that I'm sending to you is not actually a double spend transaction? And the way you could do this, one way of doing this, is by relying on hardware. So imagine, like, you have a hardware, and the person who's receiving the funds has a hardware, and my hardware will basically give you this guarantee that if I send a transaction, this transaction simply cannot be a double spend transaction. And one way to think about this is by saying that, imagine you have this Bitcoin, and the Bitcoin is held in a UTXO, and you're spending that UTXO, but the key that controls that UTXO basically gets deleted as soon as you have signed your first transaction. And because you can't sign transaction anymore using the hardware, you simply will not be able to double spend. Anyway, that's mostly it. Thanks again for your attention. And again, I'm hanging around if you have any questions. Thank you.